Well, greetings and salutations. I'm going to try and make this as quick as possible. I don't know exactly how long it's going to take, but it shouldn't take me but a few minutes to show this. I was messing around in 3ds Max today. Excuse me. And something that's been bugging me for a long, long time. Uh, I had seen a video one time of Saturn disappearing behind the moon, and I had wondered if there was a way to apply that information to compare the globe Earth to the flat Earth. What's up, guys? And yeah, Alicia. And it's pretty apparent that from normal standard observations of the moon and the stars, that the Earth does rotate and the moon orbits around the Earth and the stars are very, very far away. Long story short, I modeled out the times. It's pretty much a well-known fact that compared to the stars, the moon loses uh, about a half a degree an hour uh, when watching it at night. As in, if you're standing in the northern hemisphere and you're looking at the moon, the uh, the stars will actually appear to move faster than the moon across the sky. This goes into the whole lunar cycle, et cetera, et cetera, et cetera. And it's pretty simple, uh, and that has to do with the fact that the Earth rotates. That's how we also get our west to east shadows traversing the surface of the Earth when it comes to eclipses and stuff like that. But when you apply that exact same math to a near moon with near stars, when on from a stationary plane, well, I'll let the model show you what it did. So here's what I modeled out, because when you actually model things out, things make a heck of a lot more sense. So I just thought I'd show you this out. Now I have two models here, and I have that spaced out among 800 or 600 frames. It starts at 100. Sorry about that. That has to do with a lining up of the animations. But these 600 frames represent 1 hour. Okay, so an hour broken up into 100 pieces. Now, what I did here was I modeled on here. I put a camera on or about Florida's height. Excuse me, front. Oops. Well, yeah, either way. On or about Florida's height. Just picked Florida. Uh, and let's see here. And that camera is pointing all the way out to the moon. And this is all to scale. Per the numbers that are given to us, by the entire scientific body. Uh, Now, mind you, I am not dealing with an elliptical orbit, nor have I slanted the orbit, nor have I tilted the Earth. This is just everything on the same plane, which I think everybody would pretty much agree that there's not going to be very much of a difference. The only difference would be, instead of it going straight across the screen, it would actually kind of go off at an angle. But nevertheless, the moon travels around its orbit at 6,000 or 3,683 kilometers per hour, and it does that in a counter when looking down from the above the North Pole. That happens in a counterclockwise fashion. Same thing with the Earth. The Earth rotates in a counterclockwise fashion. It's pretty. This is all known stuff. Now, what I also did was I put way out at a distance. It's going to be a little bit difficult to see here because it's so far out there. There. I put way out at a distance, okay, centered on here, just a ring with a whole bunch of just tick lines on it. Has no particular bearing on how many lines are on there. As a matter of fact, I think I have it. Oh, I'm sorry. I have a line every 2 degrees. I had forgotten that I actually set it to 180. So anyway, got that. Now what I'm going to use there is from the camera. The camera is looking at the moon, and what you're going to see there is over this 1 hour period, 1 hour, the moon, like I said, loses about a half a degree. Okay, and it travels. I forgot how much was 300 something kilometers in that hour, something like that, or excuse me, 3,683 kilometers, which represents this little bit of movement right here. Okay, this is all inside of 1 hour. Okay, and also inside of that 1 hour, the Earth will have rotated this much. If you can see the purple Earth rotating right there. Okay, now when I look through that, that's camera one. Now when I look through that, what I'm going to see is, let me reset the time there. These are the tick marks that are way, way, way out of the distance. And what you'll see is exactly what we see every night, which is the stars move exactly this much faster and this much further uh, with regards to their position visible to the moon. It's pretty simple stuff, and you can observe this every single night. It's even better when you get a planet or something like that because a nice bright dot, and you will see it approach from your east to your west. Okay, that's just how you'll see it. You'll see that every night. Simple. Okay. All right. So now, when you apply that exact same math to the flat Earth, now this is a flat Earth with a dome on it. Okay, have a camera also down here at Florida, and I actually had this the orbit set for I think it's tomorrow. Um, anyway, it's approaching the bottom of the Tropic of, or it's approaching the Tropic of what's the south one? Capricorn. Um, Nevertheless, and I have it at 5,000 kilometers up. Camera sitting at Florida. Now, since you are on a stationary uh, disk, which flat earthers claim, well, most flat earthers claim that the Earth is, um, in order to match even the star observations, the stars have to rotate the exact same amount. They have to rotate the same amount as what we would consider the Earth to rotate, which is 1 hour and 50, or excuse me, 23 hours and 56 minutes for every 360-degree rotation. And what that does is that rotates this gray that you see here is actually that dome. Okay, and that's how much the stars would have rotated in that hour. They would have to. Okay, and then that times 24. Well, actually, the 1400 whatever minutes that I originally had this modeled for, that's how much that they would turn. Now, what I also did was I made sure you will see a comparison here between, this is the moon, and just watch this line right here as I'm going along. You'll see that it's losing that half a degree along that same math. Okay, it's losing the half a degree, meaning that the moon is moving slower than the stars. But then watch what happens here. Ready? This is what I wanted to find out, and this is what I ended up finding out. Now watch. This is the moon, camera looking up from Florida across flat Earth, zoomed in, of course. These are the vertex lines of the dome. Okay, and what you see in very little time, how far the moon moves, and it moves even though it's actually rotating slower than the dome. Parallax will make it look like it's going faster. And I don't need to show you what happens to the rest of this because it actually the moon actually goes down and kind of goes like this. It's kind of funny. But so And this is at any distance and at any speed. This has to do with the fact that this has to do with the angles between the moon, the person on the stationary plane, and the required rotation of the stars above it. There is absolutely no possible way that the yeah that there's no way to make it work otherwise unless you make the stars rotate at an unbelievable speed, and the only way you can do that would be to obviously make wrong observations of the speed of the stars throughout the night. And I don't mean wrong by a little bit, I mean wrong by a lot. Okay, as in a star would probably traverse the night sky inside of about 2 hours. And so this is just a short thing. And here I'll even show it to you in all four views so you can see what I'm showing here. Oops, this needs to be top view. Okay, this is the Earth to Moon view in the globe math. This is the Earth. This is the Earth to dome view on flat Earth math. And by the way, I had started working on it before, but you got basically the same stuff from the Pac-Man Earth and from just about every other one of them because of the proximity of the stars, the moon to the observer. That's just what it is. So let me just go ahead and move this by so you can see the difference between the two. On the globe, with very distant stars, the stars move from left to right in the northern hemisphere compared to the moon. Whereas on the dome, the stars move from right to left. There is no other way to show that this absolutely, positively does not function on FE. Now, let me go ahead and do this. And as for people in the southern hemisphere, we'll go like this. I'll just put somebody down here about halfway down the southern hemisphere. So that would probably be about, oh wait, this would be southern hemisphere. Now watch. Now this time you'll get it from left to right. However, you'll get pretty much the entire night sky crossing the moon, and even starting off in other weird directions. You'll get the entire night sky going from left to right, which is also not what we observe. It's just not. It's using the same measurements. All I did was I changed the position of the camera. And this is pretty much the entire night sky that would have traversed your vision and the moon inside of 1 hour. So, ladies and gents, that's all I really had for you. Long story short, no, once again, Globe Earth wins just by observing the stars versus the moon. And you don't have to believe me. Go out and observe it yourself, model it yourself, and yeah, that's pretty much it. So thank you all for stopping by real quick. And let's see. Happy International Observe the Moon Night, mate. All right. Well, like I said, I thank you guys for stopping by. I only had a couple of seconds, and because now I have to get ready for shift. So, y'all have yourselves a nice day.